Previously, we did several videos demonstrating different parts of the wireless system for hardware and software using emulations. Today, our focus is more using FPGA, Field Programmable Gate Array, and we will talk about the wireless gateway that's applied to ad-hoc networking for vehicles. Wireless devices use mobile ad-hoc networking. It requires no infrastructure to communicate. But for clients such as these group of people over here, if they want to communicate over long distance, they may need the help of a relay system, which typically is located on something more capable, like a vehicle or aircraft or something like that, to be able to communicate over long distance. And so the relay system typically are larger and they are much more capable than a handheld device. And what we're talking about here would be applicable to pretty much any type of wireless, whether you do 5G, narrowband, or satellite communication, and so forth. To demonstrate the system, we use a zinc FPGA board, and this here is the FPGA board. And on one side of it, we create a wireless network. So on the left-hand side would be the client systems, and then here is the relay system, and then on the other side of it, the right side, we connected the system through the internet using Ethernet network. The software we have discussed before, so I'm gonna skip that part. To converting from emulation system to FPGA, surprisingly, it was quick and easy, and the actual porting take only hours instead of days after the required hardware setup on the FPGA is done. We do find some interesting items, such as the FPGA system lacks accessible slots, whereas on the PCs or personal computer or servers, you have a lot of PCI Express slot that you can use to connect to the I/O, the outside wood. And so high-speed connectivity on FPGA is more complex and is not easily available. So we need to find alternative for that. And the alternative we used was the high-speed USB. The performance of the emulation system, since it's run on an x86 processor, it was fairly fast. And as you can see in previous video, we show you that, even though it did not run native code. The FPGAs, however, they have less cores than the x86 processor. They run at much lower frequency and less memory available on the embedded system. So to maintain the high quality user experience and keep the low latencies, we did some optimization for that. So I want to talk briefly about the optimization. The way that our software was architected on the emulator, the main part of it, which is performing the proxy or the gateway aspect of it, run the majority of the code. But to the I/O subsystem, we created interface layers. Here on the wireless side, we created what we call the app interface. And we plug in the wireless stack, hardware and software-wise, through this interface mechanism. Okay. Same thing on the Ethernet side. We also connecting that through the interface layer. The advantage of this is there are many different types of wireless and different frequency and so forth, and different modulation scheme and all that stuff. the interface layer helps us isolate the main system from all that stuff and allow us to plug in just about any type of wireless. And we can support different frequencies and so forth relatively much easier. But now to run on an FPGA, the performance FPGA become an issue. So what we did, and we did this relatively painlessly because we had this interface layer, we delayered the code. Essentially, we merged what was different process or different threads or different apps. We merged them into the same application, and we still maintain the interface mechanism. So this was done relatively quickly in a matter of hours. And before the optimization, we can clearly see that, for example, we play multiple videos in parallel. We can see that the video was coming slowly. But after the optimization, it make no difference. And as you can see, we'll see in the demo be shown you later on. And so we maintain the application binary interface. The demo will be shown very quickly. The reason is we try to keep the video short, and it can be difficult to understand. So I will explain that just a little bit. There are three parts to the demo. The first part is to boot the system and to configure the FPGA system with the Linux, and creating or making the connections with the client. The second part is we use the client, which is a window-based client, and browse the internet while playing multiple videos simultaneously, and to show the performance in real time. The third part of the demo is to capture some network traffic while we do the browsing of the internet, and we will analyze the packet. Mainly, we want to show that packets actually transition from the wireless port to the Ethernet port on the other side, and vice versa. And that communication was relatively low latency and fast, and that the system, in fact, treat the traffic and act like a gateway or relay system. And so with FPGA system available, we really excited about this because it opened up a lot of exciting possibility for us. And the next part of video, we will show you the demo.
So today I'm going to show a demo of complex wireless gateway running on embedded system, which is Xilinx UltraScale Plus FPGA board. As seen, I'm connected to the FPGA using serial port connection through PuTTY. I'm going to turn on the FPGA now. As we can see that there are some messages printed on the serial port which shows that the FPGA is up and booting is in process. I have also installed Ubuntu Linux operating system on the FPGA board. So once the FPGA is booted, we should see the Ubuntu Linux operating system on FPGA. I will also use root as login to the FPGA once the FPGA is booted up. So FPGA is booted up and I'm using root as login. Next, I will install wireless adapter driver so that we can have wireless interface on the FPGA. We can check our wireless interface is up or not through if config, and we can see the wireless interface is up. Now with the help of network manager, I will create the hotspot on FPGA so that we can connect different systems to the hotspot network. This is the interface name, and The name of my network will be LFPGA, and I'll also provide password for the same. This should create the hotspot on FPGA. As you can see, the hotspot was successfully activated. We can also log into the FPGA through remote desktop login, and the IP address is 215 as seen here. I'll use LeWiz as a username to log in on the FPGA. As you can see, we are now logged in to the FPGA through remote desktop login connection. Next, I will go to the directory where I have my gateway code. Before running the gateway code, I will do a tcpdump so that we can see the pcap files both on the wireless and Ethernet interface. So this is the interface name, and we will save this file as test wi-fi.pcap. Similarly, I'll do the same for Ethernet interface. And we will give the name as test ethernet.pcap. So as you can see, both the interface are being listened and pcap file is created. Now I will run my gateway code, and I will give the IP address as which is the IP address of my interface, and 12,000 as the port number. So you can see the proxy code is running as well. Now we'll move to the wireless client system, and we will connect to the hotspot and browse some internet sites. So we are on the wireless client system now, and I'll connect this system to the hotspot that we just created on FPGA. By the time this gets connected, I'll change the Mozilla Firefox settings so that we can use the proxy server. So I will go to settings, general settings, and at the end network settings, and we'll provide the IP address, that's the wireless interface IP address of FPGA, and the port number is 12,000 that we just used to run the code, and I'll do OK. And next I'll also clear the history so that we do not load any website from the cache. So I'll just delete all the history. As you can see, we are already connected to LFPGA network. Next I will browse to google.com, and we can see the homepage of google.com. Let's go to youtube.com, and I'll play some videos on youtube.com. So the videos are already loaded, and so I'm trying to play this video. As you can see, the video has already started to play. Next I'll go to amazon.com. This site contains heavy images, and we see that the uh, website is already loaded. I'll just mute the video so that it doesn't interfere with my voice. I'll try to play a video on Amazon as well. So we'll go to Prime Videos, and we can see any video trailer. So the movie videos for movie icons has already loaded, and I'll select this video, and I'll do a watch trailer. As you can see, the video on the YouTube is already playing, and the trailer is loading on, and the video already started to play on Amazon as well. Next I will go to yahoo.com, and here we'll go to sports section. So as you can see, we are in the sports section of yahoo.com, and I'm trying to look up some videos on sports. Just browsing to see if we have any video on this page. I don't think we have any video on this page, so I'll just go to soccer and let's see if we have any videos on this page as well. Okay, so we have this video and I'm going to play this video. So here the video is being loaded, and as we can see that the video is already running on Amazon Prime and the video is already running on YouTube as well. And we are trying to load the video on yahoo.com. So the ad has already started to play. So thus we can see, like, we can play videos on 3 simultaneous websites. Next I will show you the pickup file that we just captured on the FPGA, and we'll try to compare the pickup file on wireless and Ethernet interfaces. So I've pulled up both the pickup files. test_wifi.pickup is the pickup file on the wireless interface, and test_ets.pickup is the pickup file captured on the Ethernet interface. Now whenever I was browsing different website, my terminal is printing the website name, its IP address, and the port number that it used for connection. So here on the wireless interface, I will use 65143 as the port number to filter out packets. And here I can see that there was a request for connection to www.google.com. Similarly, I will put the IP address 172.217.164.100 as a filter on the Ethernet side, and we can see that there's some encrypted data. Now we will just compare the client hello data on both the wireless interface and Ethernet interface. So on the wireless interface, I get the request from 10.42.0.167, which is the IP address of my client, to 10.42.0.1, which is the IP address of my gateway wireless interface. And if we just scroll down, the ending pattern over here is 8A E2227B, and we will compare the same on the Ethernet interface. So this is the client hello message, which goes out from 192.168.7.215, which is the IP address of Ethernet interface of FPGA, and it goes to the IP address of Google. And this is the client hello message. So we will also compare the data over here. As you can see, the ending data on the Ethernet interface is 8A E2227B. Thus this proves that the data is forwarded from wireless interface to Ethernet interface, and then it goes to the remote server. Thus I intend to show the working of wireless gateway on embedded system, which is Xilinx Zinc UltraScale Plus FPGA board.